Okay. So, hi, AP Chemers. Yeah, it's Tuesday, the 22nd of March, and we're going to finish up chapter 7 today. I know, but you know what? It's pretty short and it's not really very hard. So, I'm going to show you the calculations that you need to do with the equations that you need, how to do some of the stuff, and then we're going to just end our video there. And on Thursday, I'll send a video out that will be more of chapter 8, the very last chapter in the book. Okay. Chapter 8, by the way, is long, but there's a lot of stuff in it we don't need. So don't be too depressed when you look at the length of chapter 8. But chapter 7 is only like 35 pages. For you at this point, that's nothing. Okay. So we're going to see where we left off. We left off, and I think section 7.1. Let me open my book and verify that because I marked the page when last we met. Yeah, I'm going to tell you right where we're at. So I'm on page 451. This is indeed 7.2. Sorry, 7.2. It's about Gibbs free energy. Gibbs and Helmholtz came up with that equation last time. So just a quick review. So I'll say Gibbs free energy. I've never quite understood why they call it free energy. But what it's about is, like I said last time, is something spontaneous? Does it happen or not? And if delta G is negative, we said last time, it will happen. If it's delta G is positive, it's not. So here's the, oh God, what are they calling it now? The Gibbs-Helmholtz equation. We had it last time. Gibbs-Helmholtz. I assume it's TZ because I think it's a nice, German word, I believe. And of course, she doesn't write it there. Frickin' A, there it is, Helmholtz. I'm right, TZ. So it was what? Delta G equals delta H minus T delta S. Okay, and again, delta G, if it's negative, stuff happens spontaneously. If it's positive, it doesn't. We're going to play with that today in a little bit with a rubber band, okay? So we'll look forward to our rubber band. Sherry uses a balloon. I don't know why. So if you have a rubber band, you can do this with me. You can stop the video and get one now for later on. Okie dokie. On page 451, Cheryl has an equation. I don't know why she put it here. It's this. It's the change in S of a system equals the change in H, the change in heat or heat of reaction divided by the temperature. But if you think about it, last time I talked to you, we had this other equation. You ready for this? This is a review, and it said the change in S of the surroundings equaled negative delta H over T. Now, so both of these shouldn't be as a big surprise to you because if you think about this philosophically, here's your beaker or whatever you want to call it, your test tube. We're going to call it your system. This is kind of review, okay? And surrounding it is, big surprise, the surroundings. And so let's pretend our system is exothermic, okay? So it's going to have a negative delta H. Well, that means the surroundings, maybe it's a calorimeter, maybe it's like water or air surrounding your system, that's going to absorb heat because it's coming from the system. So out here, it's going to be plus delta H, the surroundings. So if you think about it, if one side loses heat, the other gains. So if I want the change in S, which was entropy or disorder, if I want the change of that for the surroundings, it's just negative delta H over T, but the opposite, if I want the change in disorder, S, called entropy, of the system, then it's just without the negative sign, okay? Because it's the opposite sign. And we learned this, I think, earlier this year when we talked about heat of reaction and Hess's law and stuff like that, okay? And what else did we talk about? We talked about work done by the system on the surroundings or the surroundings by on the system. This doesn't have much to do with work, but it does have to do with looking at what's going on with heat. Okay, that's kind of review, but I thought about that last night and I knew I wanted to tell you about it, okay? All right, so here's the scoop ski. Back to page 451, where I ended off last time. So we're again in section 2, Gibbs free energy. A lot of times what people will do is put these little zeros here. All right. So again, just so you know, that's at standard conditions. So it's 25 degrees C and 1 atmosphere pressure for gases. Okay, that's the little zero. Means, oh God, we're going to write the standard state. Again, that's kind of review for you. The good thing is, even though we're in book 2, is you guys have learned a lot in 2 books of chemistry. Don't underestimate what you know or have heard before, okay? I know you don't have it all mastered, but, you know, you're getting there, okay? All right, I want to look on the next page at a cool graph that Sherry does. I won't do everything page by page, but this is really kind of cool because I thought about it when I saw it, and I want to talk to you about it briefly. Look at this graph on page 452. So open your book. And this sucker has energy on this side, En for energy, and temperature on this side. Okay, so here's the enthalpy. So as temperature goes up, the enthalpy doesn't change that much, but eventually goes up a little bit. So that's enthalpy. So that's delta H. All right. And then the Gibbs free energy line goes more like this. So it becomes more and more negative. And this part here in the middle, I'm going to put it in red. This is the difference. It's the T delta S. You're probably wondering what the hell I'm doing. Okay, so bear in mind, again, that equation is delta G equals delta H minus T delta S. The minus is really important here because if we have more disorder, if the disorder is if it's increasing, then if I got a minus here, that minus, of course, temperature is always positive because it's in Kelvin, right? So this term, this negative term, becomes more and more important as temperature goes up. And what that does is it causes the delta G number to become more and more negative or more spontaneous. So here we go, ready? Oh, temperature's increasing. The Gibbs free energy becomes more and more negative by how much? By this amount, T delta S, than just the delta H value. So the T delta S kind of drags this down and makes it more negative. Now, that's not true of every reaction, but it's true for one like this. Let's say I take CaCO3, we talked about this last time, and that's limestone, and I break it up into calcium oxide solid plus CO2 gas. Well, big surprise, at high temperatures, breaking something up is favored, right? I'm sure you knew that anyway, a decomposition reaction. But this proves it mathematically. Here's what I mean. The Gibbs free energy gets more and more negative, okay, as I increase the temperature. So T gets bigger, therefore this term becomes more negative, and it just happens more and more easily, more spontaneously at a higher temperature. Notice she didn't put any numbers on here. We don't know where 0 is, but you could put it somewhere in the middle of, I don't really care. Okay, you get the idea? Let's do the opposite. What if I have a low temperature? Then this term becomes really unimportant. Look at it. And therefore, what's really important is the delta H. That's what really matters at a low temperature. In fact, at really low temperatures, this T delta S term becomes close to 0. It just doesn't matter. And what really drives a reaction is the delta H. It's pretty much the same as the Gibbs free energy. Okay? So low temperature, and same with this. What's going to happen here? Low temperature with this reaction, well, it's just going to stay a solid because the delta H value would have to be really high to break it up, and it's just a big requirement. So it's not really going to be spontaneous, this particular reaction at a low temperature. High temperature, I can break that sucker up more easily. Anyway, I like that graph, and I wanted to point it out to you on page 452. Okay? All right, now, Sherry gives you 2 ways to get delta G, and I want to talk to those 2 ways. I sound so German. Talk about those 2 ways to get delta G. Okay? First, the easy way. She does this second. I don't know why. The easiest way to get delta G is to just find it by this. You take delta G equals the G of the, you guessed it, Chester, products minus the G of the reactants. Big surprise. We've done that so many times, right? That's the way to get it. Where do? You use the data from the back of the book, and you're going to have to do that in some of these problems. So Achtung, I'm going to give you that page again. It's a lot of data, but it starts on page 570. Page 570. So use page 570 data. That's the easiest way to get standard temperature delta G. Okay. Later on, I'm going to show you how to change delta G if it's not standard temperature. It's not a big deal. Okay. Ute. Here, let's label this. How to get delta G. Luke, use the equation. 1, 2. Here's the longer way, and sometimes they'll have you do this in parts on an FRQ in the on the AP test. Okay, the longer way goes like this. Same thing. Use page 570 data to get delta H with, you ready? Delta H equals the H of the products minus, big surprise, the H of the reactants. See what I mean about this chapter not being all that hard conceptually? A lot of it is products minus reactants. Okay, but you're not done yet. Then you're also going to get delta S with data from the back of the book, and you're going to go and use this. The delta S at standard conditions is the S of the products minus the S of the reactants. Sprad minus react. Okay, or something like that. But you're still not done. Can you see why I prefer method 1? This one just takes a lot longer. So you got this, then use delta G, the Gibbs-Helmholtz equation. Delta G standard equals delta H standard minus T delta S. You might say, but what do I put in temperature? Well, the temperature is 25 degrees because it's standard. So it's 25 unless they tell you, or cross it out, 298 Kelvin, unless they tell you otherwise. So unless they give a temperature. You okay so far? So again, it's plug and chug, and plug and chug, essentially. So get these two with data, products minus reactants, and you do have to put in the number of moles, like if it's 5 moles of a product, multiply by 5, but you know that already, right? Because you've done that all year long and you've done it successfully. Then you got to use the Gibbs-Helmholtz equation and put in the stuff in for delta H0, for delta S0, and for the temperature. Crank it out and see what your delta G is. Much nicer to do number one, but sometimes on the AP, can you guess it? They'll have a question finding delta H, another question finding delta S, and another finding delta G, right? 2 points apiece or whatever. So sometimes that's an FRQ, just so you know. Huge. I think we went over that yesterday, so I'm not going to bother. Okay, here's something good to know. You ready? Cheryl doesn't, I feel, say it clearly, so I want to say it really clear to you. Ready? I'm going to do it under a psst. Hey, kids, guess what? You know those values at the back of the book that are 25 degrees? Well, the delta S and delta H values are pretty much the same, even at different temperatures. So the delta H and delta S values in the data tables change little with temperature. So the beautiful thing is, if I want delta G at a different temperature, really all I got to do is put in a different temperature. You don't need new data, is what I'm trying to say. So put in a different temperature in our favorite equation in the universe, delta G equals delta H minus T delta S. And I'm going to circle temperature. So that's all you got to change if it's not at 25 degrees. Just a different T. Isn't that great? You don't have to dink around with new data. It's the same data. It changes very little. And I've never heard of anybody that bothers getting different data than just using a standard temperature data. Okay? At least not with anything we're doing. Ute. Ute. That's it. Rubber band. You ready? Okay, so here we go. We're going to do this in our books. I'm on page 462. It's got the little pressure, equilibrium, and free energy. It's the start of section 7.3. I think of it as the rubber band section. Section 7.3. And she uses a balloon. Again, I'm going to pull out my rubber band because I find a balloon under your nose highly embarrassing. It's really much more honorable to have a rubber band under your nose. Ready? Here we go. Doesn't that look better? Okay, so if you got your rubber band, if you don't, stop and go get one. Now, you're going to do this on your upper lip. Why? Because your upper lip is very temperature dependent, so biologically. So I'm going to rest it on my upper lip and pull this out and then feel the temperature difference. And now I'm going to let it go in and feel a different temperature difference. Well, I wish you could do this with me. Probably you're doing it now. So does it feel warmer or colder when I do this? Oh, it feels warmer. Now stretch it out and now release it, but keep the rubber band on your lip. Oh, it feels colder. That should seem sort of weird to you, except if you think about it. I know it's not a reaction, but it's a process. And so the process is thermic this way. Oh, gets hotter. So it's exothermic. And here, when I let it go and I let it go to unstretched, it's cool. It's endothermic, if you think about it. So this way it gives off heat. I can feel the heat on my lip. This way it takes heat from my lip and my lip feels cooler. So try that. I know I look bizarre, but I'm not there to worry about it. So in other words, we don't have to do the whole thing for you. I wouldn't want to spoil the warm up, but in the warm up, so the delta H, and we got stretched, or we got unstretched. And for the stretched, remember it gave off heat. So it's going to be a negative value. It's exothermic. And when I unstretch it, whoop, that made it cool. So it's pulling heat away from me. So it's endothermic. Don't believe me? Try it. Get that rubber band on your lip. Well, now let's think about the delta G, the next column. Well, look at your rubber band now. Which is spontaneous, stretched or unstretched? Yeah, unstretched is spontaneous. That means it will be what sort of sign on the delta G? Let me repeat that. So unstretched is spontaneous, therefore that's a sign for the delta G. Spontaneously was a negative sign. Oh, bizarre. And therefore stretched is not spontaneous because I got to put in effort to stretch it. So that is not spontaneous. So that process is a positive delta G. It's non-spontaneous. Well, think about our equation now. There it is right up above. Delta G equals delta H minus T delta S. Why am I thinking about it? Because you guessed it, Chester. I'm going to put the last one, the delta S value here. And now we can work it out mathematically. All right. Look at the first one. If delta G is positive and delta S is negative, well, the only way to get a positive delta G is the delta S has to be what sign? It's already a negative in the formula, so the delta S has got to be negative, doesn't it? Hope I'm right. If I'm wrong, you'll have to tell me in class. Let's make sure of that. So minus times a minus would be plus, and if the delta G is plus, then this side is winning. And I have to have plus here because the delta H is minus. And the overall delta G, we know it's stretched as not spontaneous, so that's positive. Isn't that wild? So we figured out what's going on with the molecule. Okay, and for the opposite, it's going to be just the opposite, isn't it? Here, the delta, if it's unstretched, it's spontaneous, so the delta G is negative. And if it truly was endothermic, then that's positive, the delta H value. So therefore, the delta S got to be positive too because I have a negative in the equation. Okay, now let's think about what that means. So representation means picture. Some of you had organic last year will probably know rubber and stuff has long lines of carbons, isn't it? So let's think about what's going on. So If it's unstretched, it's positive entropy. That means there's more disorder. So if I could look close to this, I've got lots and lots of disorder. And if I stretch it out, I have less disorder. So if I stretch it, I lose disorder. In other words, I am more ordered now. If I'm more ordered, think about what that means. Here's the little atoms. That's my picture. That's pretty ordered. Let's do the second one. Ready? Disordered. Okay, so more. So how about this? And all that together must be how my rubber band looks up close. Isn't that wild? So look at, I got much more disorder in the rubber band. I know how it has to look if I think about it logically. Whereas the ordered one has to be more straightened out. And we got all that, frankly, from two things. From the delta H's that you can feel. Hot, cool. All right, exothermic, endothermic. And the fact that if it's unstretched, that's obviously favorable. So that's a negative delta G value. Negative is spontaneous or favored. Okay, isn't that cool? All that from a stinking rubber band or balloon if that floated your boat better. Then you can answer some of the questions there later. Okay? Ute. I love that. I love that activity. I'm sorry I wasn't there to do it in class. It's a lot more fun. So sometimes students shoot rubber bands at each other, but I digress. Let's continue. And believe it or not, we're coming down to the end. The end of what? The end of chapter 7. Ha! It's not long. I know. Shut up, Mr. Weiss, and just finish. All right. Okay. I love chapter 7 because it just makes sense. I'm going to put my rubber band back behind you. Don't slip on that. Okay, here we go. Here's a correction, okay? A way to get the delta G if it's not at standard conditions, in other words, not at equilibrium. Here's the equation. So you take you get delta G by first taking the delta G at standard conditions, and then you're going to add to it R times T times the natural log of Q. Remember Q? The little brother of K, but not at equilibrium? That's why it says the delta G at not at equilibrium. You get what I mean. And the R value's got to be in joules to agree here. So make sure your labels work. So it's 8.31 joules per, I think, mole degree C, mole degree K, mole Kelvin. All righty. Yeah, so that's a little correction that you can use sometimes. Is it that important? No. Is the next thing I'm going to tell you important? Yes. Star. It's time for the rat link. You ready? The famous rat link equation. Rat link equation equates? No, that's not the word I want. Joins, relates. The equilibrium constant, capital K, remember Q's big brother that is at equilibrium, with delta G. Is there a relation there? You better believe it. So here's the rat link equation. You ready? And this is really an important one. Let's put it in red. Can you guys see red? Nah, maybe black. So it's the delta G at standard conditions equals R times T. Oh, that spells rat. That's where the rat comes from. And ready? Natural log of K. Oh, link. Rat link. Get it? But shame on me, I forgot the tail on the rat. Ready? Here we go. We're going to put the tail on the rat. That little equation is worth its weight in gold because you can change any equilibrium constant to delta G at standard conditions or back and forth. All right, isn't that cool? It's called the rat link because it looks like a rat link. And don't forget the little minus sign. That's the tail on the rat. Okay, I know. I might as well have a good time. I'm stuck here with Corona. What else can I do, right? Let's look at one equation using this just to wrap stuff up, because that's really all I need to talk to you about. And the equation we're going to look at is on page 466. I'm going to erase this a little bit. Let's look at her sample. And she's got the K. She wrote it kind of weird. The K is 24.0 at 25 degrees C for this equation, okay? I got PCl, oh man, 3 plus 2. 3 plus Cl2 makes, big surprise, PCl5. Okay, so there you go. I can make all my L's the same if you want. PCl3 plus Cl2 makes PCl5. So it's a 20. So the question is, can you get the delta G at standard conditions? And the answer is, yay, verily, they cried. And how do I do it? I use the rat link equation. So the delta G standard equals negative RT natural log of the K. Or it could be a KA, or it could be a KSP, any of those K things. They're all Ks, right? They're all numbers that are greater than 0 and can be some really big number or whatever. And don't forget the minus, don't forget the tail. So what's that equal to here? It's negative 8.31 joules per mole Kelvin times 298 Kelvin times natural log of 24.0, which, and I'm going to believe Cheryl here because she's got it, is negative 13,800 joules per mole. And that's exactly the label I should get. The kelvins cancel, and I get joules per mole. Or if you like, change it to kilojoules, because that's the way we usually got delta G's. So it'd be negative 13.8 kilojoules per mole. In other words, hey, look at that K. Remember K? K is 1. No, K is 24. Therefore, the products are favored. So if the products are favored, I got a number bigger than 1. This should make total sense to you. That means it's spontaneous. And if it's spontaneous, the delta G should be negative. And it is. In fact, it's pretty negative. It's negative 13.8 kilojoules per mole. So yes, these two things tell you the same thing if you think about it. The delta G being negative and the K being over 1 both say, hey, the reaction is spontaneous at this temperature. So in this case, at 25 degrees C. Isn't RATLink handy? It's a connection from an old concept, equilibrium, to a new concept, delta G. So once again, think about it, all right? If K was bigger than 1, your delta G is going to be negative. What if K is less than 1? Then your delta G is going to be positive. Exactly right. Let's make a little chart of that just for grins. Because that's a useful thing to like complete this chapter in our head. So delta G and K. So if delta G is negative, then it's spontaneous, then the K is going to be greater than 1. And if delta G is not spontaneous, so a positive value, then the K is going to be something less than 1. Beautiful. What if K is 1? If K equals 1, highly unlikely, but it could be 1 on the way to something else, like a Q or something, never mind. The delta G will then be 0. You're going to solve some problems with that, okay? That's a useful thing. So if K is exactly 1, or even if it's Q at that point and not K, then the delta G would be 0 at that point. Can I tell you where we're going with that? For example, find the temperature where reactants are favored and we're going to use the same equation. Ready? PCl3 plus Cl2 forms PCl5. This is, again, it's not in your book, but it's using the same data. So on the previous page, it's from page 466, okay? So what do? Find the temperature. Well, guess what we're going to use? We're going to use, ready? Delta G equals delta H minus T delta S. If I want just where the reactants are favored, I'm going to put in 0 for that changeover point. 0 for delta G. You ready? So 0 equals the delta H we'll have to solve for. I don't have that data. Minus T delta S. So I'm going to put a little star here because I can't finish it because I don't have the data without looking up a lot of stuff in the book, which I don't want to take time for. But if I found the delta H by looking at the data in the back of the book and the delta S by looking up the data at the back of the book, then I could solve for T, the temperature where the equilibrium just starts to shift from products, remember the K was 24, back to reactants. So maybe it's a colder temperature, who knows, all right? So my little star, I'm going to say here, use delta H and delta S data from back of book. and then solve for T. And that T will be the changeover point. So you could say, whatever, temperature's less than whatever T is, right? Yeah, that's pretty much chapter 7. The only thing I've ignored is a word. Well, 2 words from Cheryl. And I'm debating as I teach you as to whether I want to ignore them. And you can probably already tell I'm not going to ignore them because Cheryl uses the words. So I guess I probably ought to tell you what they are. Except I just lost where she defined them. And I never use the words, so I don't usually have them in front of me. I thought it was right here at this balloon thing. Okay, can I get him at the back? Earth to Cheryl. Earth to Cheryl. Come in, Cheryl. Do you have the words that I want? No, she does not. Well, the words are exergonic and endergonic reactions. And I've never used these words in my life, but she does use them a little bit. So perhaps I can look back and get a definition for you. But I'll be darned if I remember off the top of my head what they meant. And I'm looking frantically in these 2 sections to find it. You would probably find it quicker than I. All right, maybe I can find the index and actually locate it. Oh yeah, we should talk about coupling too. Let's see if she's got an index. She doesn't have an index. So I'm going to just punt and I'm not going to worry about it. You can read about exergonic and endergonic from her. But I should talk about coupling. Coupling is not what you think. Get your mind out of the sewer. Okay, so here we go. What is coupling? Coupling is making something that's not spontaneous spontaneous by coupling it or adding it to a reaction that's very spontaneous. So making a non-spontaneous reaction spontaneous by coupling or adding it to, coupling the reaction to other reaction or reactions that are spontaneous. Okay, and again, non-spontaneous, so we're talking about a positive delta G, and we're coupling it with reactions that are spontaneous, so they have a negative delta G. It's kind of a math game, isn't it? I'm trying to make something negative, spontaneous, and if it's positive, I got to add more negative to make it positive. Okay, so one industry that does this, and the biggest one you probably need to know about worldwide, is the steel industry. So what we're trying to make is iron metal, which is really not spontaneous. We're getting a little bit of carbon in with the iron, but mainly we're trying to make iron metal. So what do? They burned coke, not Coca-Cola. Coke is like a form of carbon. And when they burn coke, they get CO2. So, you probably know where I'm going, right? So to make the iron, that's a non-spontaneous process, so it's a positive delta G. Making CO2 is very spontaneous, unfortunately for our planet. So it's a negative delta G. So when we make steel, we also make a lot of CO2. And I believe another process that also works this way is making concrete. I have to look that up to make sure of it, like Beton in German, right? So I'm making concrete. I think it's the same way. I have to like make a lot of CO2 and then I can get the concrete. So it's pretty stinky. Even something that doesn't sound bad, making iron, ends up giving off a lot of CO2 because we use coupling to make the process spontaneous enough to happen to get iron to build stuff behind your walls, right? To build your steel structures that make up most of the buildings that we're in. So it's hard. We want good steel structures, but to get steel, you got to burn a lot of coke to get CO2 to make the whole process overall spontaneous with this idea of coupling. Good. My people, that is chapter 7. I will start chapter 8 next time with you. It's been a pleasure. Look at that, 46 minutes. I didn't even waste an hour of your time. I hope that helps with the problems in chapter 7 and try to get there as lickety split as you can. Just a reminder, clausura is April 4th. So I know it's a stressful time. I wish I could be there, and I will be there certainly, I hope, on Monday. Okay, I'll try and test free on Saturday. All right, all of you, bye. You can write me questions through email or the AP chat. Okay, I'm happy to answer your questions. Okay.